So this question that we have here, we have to prove by mathematical induction that n to the power 2 plus n is divisible by 2 here. So the first step that we'd have to do here is we need to show that this is true when n is equals to 1. So here we say that, so step number 1 here, so we need to show that it's true when n, or for n equal to 1 like this. So we get this expression here, we have n squared plus n here. Then we substitute where there's n, we put a 1 there, so we have n squared will be equal to 1 squared plus 1. So here we have 1 plus 1, which will simply just give us 2 here. So if we divide 2 by 2 here, we're not going to get any remainder, so the answer that we're going to get is just simply 1. So therefore here we say this is true for n equal to 1 here. So therefore true for n equal to 1 like this. So we go to step number 2, which is the inductive hypothesis. So there we're going to make an assumption that the statement is true when n is equals to k. So mean that if that statement is true, we equate it to 2 by any variable of our choice there. So here, the inductive hypothesis So on the inductive hypothesis, we assume that, or make an assumption. So we assume that it's true for n equals to k. So here we have k squared plus k. We equate it to 2m like this here. So we can make it any variable, either x, a, b, or any variable of our choice there. But here, let's go with 2m. So here, we make k to the power 2 the subject. So if we make k to the power 2 the subject, we're going to have 2m minus k like this here. So after doing this, we go to the third step, where we have to show that the inductive hypothesis is equally true for n equals to k plus 1. So here we just put a statement there. So we need to show that it's also true show that it's also true for n equals to k plus 1. So here we get this expression the same way it is there, then where there's k, we just put k plus 1 there. So we have k plus 1 squared plus k plus 1 here. So we just start simplifying this here. So when we expand what we have here, we're simply going to have k to the power 2. Let me just erase that. Okay, so here we're going to have k to the power 2 plus 2k plus 1 like this here. Then we still have the k plus 1 this side, so we have our k plus 1. So we have our k plus 1 like this here. So then here, this expression simply becomes k squared plus 3k plus 2 like this here. Now remember I said that k squared is simply equal to 2m minus k here on the inductive hypothesis there. So we substitute with the same there. So we have 2m minus k plus 3k plus 2 like this here. So negative k plus 3k here was simply going to get 2k. So here we have 2m plus 2k plus 2 like this here. So here we can just factor out the 2 because it's a common constant that we have there, or coefficient rather, that we have there. So here we factor out the 2. So 2 open brackets m plus k plus 1 like this here. So therefore, if you let m and k be equal to any variable of your choice, let's say m is equals to 1, k is equals to 2, so we're going to have 3 plus 1, that's going to be 4. Then whatever number we're going to have in the brackets, if you multiply it with a 2 and divide it by 2, we're not going to get a remainder there. So now, if that's the case, then we just conclude to say what we have here is equally true for n equals to k plus 1. So therefore, true for n equals to k plus 1 like this here. Okay, so now if this is true for n equals to k plus 1, then this holds under mathematical induction for every natural number n there. Okay, let's go to the next question.